Hello, good morning. How's everyone doing today?
Good morning.
Morning, everyone. All right, so we have a couple more problems left for solving static equilibrium situations. So we will do that. And then we will switch to universal gravitation. After rotation, we have three more topic left. One is the universal gravitation, and then simple harmonic oscillation. And the last would be our fluids, okay? All right, so let's take a look at this problem. It's a very common type of question you will see for static equilibrium. It's probably, it looks similar, right, to the lab that you have already done. We have done one of the lab that looks like this with a bridge simulation where you would have to measure the different distances and the angle. All right, so here you have a beam, and right here you have this hinge mounted to the wall. On the left-hand side, you have a object, a sign that you have the hand over there, and the whole thing is being pulled by a rope. So it's right over here, okay? They give us some variables. We know the beam's mass, we know the sign's mass, we know the length of the beam. We also know this rope is attached 2/3 of the way of the beam. And the angle right here is 34.1 degrees. So here's what we're given. We want to calculate the tension in the wire. So we have talked about the general approach in solving static equilibrium questions is, first of all, draw all the forces. Draw all the forces and also label the distance for each of the forces. You want to find the perpendicular distance that the force is acting on so you can calculate the torque. We call that an extended free body diagram, okay? So I want you to all, let's work together to complete this extended free body diagram. So whichever force you can think of, let me know and we will put it on the picture. What kind of forces should I draw?
So there's a force from gravity from the block.
Okay, so I will draw a force here, gravity of, oops, I don't know why this is not working. I have just charged it. Let me just charge it again. All right, okay, so that's one. I'll write it down later. That is MSG, the gravity of the sign. Very good. What other forces should I draw?
There's tension from the rope.
Very good. In what direction is the tension?
I would say in the horizontal left direction.
Very good. It's horizontal and the tension is trying to pull it, right? Pull it back. So it will be pointing to your right-hand side. It's toward the wall. Okay, so we should have a tension. All right. Are there any other forces that I should draw?
The weight of the beam.
The weight of the beam, very good. And what position should I put this weight of the beam?
Because it's a uniform rod, or that's our assumption, I guess. At the very middle of the beam, so L/2.
L/2. Okay. All right, very good. And are these all the forces? The three forces are the forces we need to draw. Are there anything else? Is that all? There's also, Rosali said, is there a torque about the hinge? Yes, so from the hinge, definitely there are some forces that is acting on the beam. So we could draw the forces from the hinge. Notice that we don't really know necessarily exactly what direction the hinge is pointing at. So we could just assume there's going to be some horizontal forces and some vertical forces. So we don't know exactly where, but we can just draw hinge X and hinge Y. Okay, so sorry, I had to switch the screen, what you're seeing, because I need to get my pen charged again. All right, so these are the forces. I will put it on later. Now let's think about the level arm for each of these forces. Okay, so let's think about the sign, the weight of the sign. The weight is directly downward, and the level arm would be this entire horizontal distance. Okay, that's the distance that's perpendicular to my weight. Okay, so look at this distance. What do you think that distance would be? We know that the beam has length of L, but I don't want the beam's length. I want the horizontal distance. Knowing that the beam makes an angle theta with respect to the horizontal, what would you draw? What would you say that the horizontal distance, the level arm is for the weight of the sign? It would be L times cosine theta. Very good, Rosali. It is L times cosine theta. That is one level arm for the weight of the sign. Very good. Now, likewise, you can see the second level arm we can put on would be the level arm for the weight of the beam. So the weight of the beam is just like the weight of the sign, but it's simply halfway. Right? It's at L over 2 point instead of all the way to the end of the beam. So likewise, the level arm for the hinge would be level arm for the weight of the beam would be L over 2 times cosine theta. Okay, just half of what we had before for the weight of the sign. So those are the two. And the level arm for the hinge, you can see that, well, the hinge, depending on where you think the rotation is, it looks like we have, by default, think about the rotation relative to the hinge, right? So if we're talking about, if we're rotating around the hinge, then there is no level arm about the hinge. So you don't have to think about the torque that the hinge applies. Okay, so that makes it simplify some situations. The one thing that's left is the level arm of the tension. Tension is horizontal, so the level arm will be a perpendicular distance. So it will be this vertical distance, which is where that dashed line across the wall to the yellow dot where the hinge is. So that vertical distance is a sine theta, right? In that triangle is a sine theta. And you can see it's the hypotenuse times sine theta. The hypotenuse is the entire length, 2/3 of the way of the length of the beam times the sine theta. Okay, so if I put every forces on here, you would end up with this extended force diagram. Okay, so 2 gravity, 1 tension, and the force from the hinge, since we don't really know in what direction it is, we're gonna assume there is some horizontal component and some vertical components. We could call it HX and HY. And these level arms, we talked about L cosine theta, L over 2 cosine theta, and the 2/3 L sine theta are the corresponding level arms for each of these different forces. Now, if you labeled everything, now when you go ahead and try to write down your torque equation, it becomes much more simple. So before we move on to talk about our torque equation, are there any questions about this diagram, how we came up with this diagram and the distance?
Could you briefly explain where the L cosine theta came from? I'm sorry.
Yes, absolutely. Okay, so now let's go to my this screen that I could draw it on here. So this is the gravity you were looking at, and the level arm is this distance. So it is from the rotation to where the force is, and you want the perpendicular distance is this distance. And this distance, this is theta, because this is theta, right? So this is theta, because these two lines are parallel to each other. And this entire length hypotenuse is L. So that's why the horizontal distance is L sine theta.
Okay, I see. Thank you.
Okay, sure. And you can see this distance from here to here will be 2 over L. I'm sorry. This distance we don't really care. We wanted the half of the way, the mass of the beam is we want this distance, and that is L over 2 cosine theta. Now this distance is 2/3 L sine theta. Okay, so that is what we show in this diagram over here. Okay, so now we have all our forces and distance. We're ready to write down force and torque equation. We can start with the torque equation. Like I said, I don't really know which equation is easier to work with right away, but I can always start with one and see if I need more. Okay, so in this case, I realized, well, to write down the force equation, you need to add up the forces of the hinge, right? But I don't know the force in the hinge. However, if I do choose the torque equation to start first, I realize I'm rotating relative to the hinge, so the torque from the hinge is 0. And I think that is where I should start, because I don't need to worry about the hinge torque. And the only unknown is the tension. So I think the torque equation would allow me to calculate the tension. Okay, so that's why I want to start with the torque equation, but sometimes it's not so obvious. And if it's not too obvious, you just start with one and see if you need more. Now we'll start with the torque equation. You know you need to add up all the torques from the sine, from the beam, from the tension. They add up to be 0. Okay, and the hinge has 0 torque, so I don't need to include it. Now let's write them out one by one. Would anybody be able to tell us, how do I write down the torque from the weight of the sine, the mg right here? You use distance times the force and give it a sign, whether it's positive or negative. Positive being counterclockwise, negative being clockwise. So how do I write down this first term?
For torque of the M, that's an S, right? MSG?
Yes.
Okay.
MSG or yes, MSG, or you can use different M's, a capital or a small lowercase m. Let's just call MSG then. Yeah, MSG.
Okay. The torque for that one and for MBG would be positive.
Okay, so so this one give you a positive torque, you said, right?
Yeah.
Okay, so positive, and the level arm is L cosine theta. So that would be my first term, right? This is the torque from the sine. Is that correct?
Yeah.
Okay, very good. Now let's do this one. The torque from the weight of the beam itself. What should I write down?
The mass of the beam times gravity, and then multiplied by the lever arm, which is L over 2 cosine theta.
Excellent. And is that positive, Grant?
Yeah, you want to make that positive because you made the other torque positive and they're both counterclockwise.
Excellent, thanks so much. These two, we got it very good. Thank you all. Last term is the torque from the tension. How do I write that? How do I write that one?
Just because the other ones are positive, this one we know it has to be overall negative.
Okay.
So we could just go minus torque sub k, or smaller t.
Okay.
Or yeah, and then we could just solve everything and then solve for that.
Okay, solve for the torque of T. I want to solve for the tension, right? So the torque from tension is T negative, very good. It's going to make it clockwise, negative T times the level arm. And we had labeled the level arm there is 2/3 L sine theta. Very good. Okay, so at this point, you can solve for tension. You can cancel the quantities that they all have in common, and you can solve for tension. So tension is ms g cosine theta plus mbg cosine theta over 2 divide by 2/3 of sine theta. Okay, so you could cosine theta over sine theta is cotangent theta. You can further simplify this to be cotangent theta. So the tension is this. Okay, this is our tension. So cotangent theta over is coming out, and then simplify the equation a little bit. That's your tension. You can plug in the numbers at this point to get the number for the tension. Okay, so we realize, okay, it looks like using only the torque equation is enough to solve for the answer the first question. So that's the first one. Now let's move to the second question, asking what is the net force that is provided by the hinge? So the hinge provides a force in a direction we don't really know exactly where, but we know it may have an X and Y component. So if we can solve both of these components, right, then the net force is simply the X component square plus Y component square and square root of that. And we will be able to answer the second question. So we realize, okay, in order to answer, to find Hx and Hy, we need the force equation. And at this point, we are confident the force equation can give us both Hx and Hy, right? Because all the other forces are already known. Tension, you just solved it. You know the gravities. So the only unknown quantities are Hx and Hy. And I should be able to get two equations. One is to sum up all the forces in the X direction, right? One is to sum up all the forces in the Y direction. So I should be able to get two equations, and I have two unknowns, Hx and Hy. So I know I'm able to solve it. All right, so let's sum up all the forces in the X direction. Assuming to the right is positive, you take a look at all your forces in the X direction, you realize really just have tension and the hinge force X component. So, all right, it looks like Hx has to equal to the tension you just got. That is the first equation. The second one, let's sum up all the forces in the Y direction. Well, simple enough, Hy is pointing upward. The mass of the sine and the mass of the beam all points downward. So these two gravities are going down, right? So they add up to be 0. So the hinge force Y component has to equal to the weight of the sine and the weight of the beam combined. All right, so we solve for H of X and Hy using the force equilibrium. Okay, and then you could plug it in to get your overall H. So that's pretty much it. last question has to do with if you have a maximum amount of tension. Think about if you were to doing this in the more of an engineering design, you know that how much the wire can endure, how much force the wire can endure before it breaks. Then from that, you can plug in the maximum tension you can handle. And then that will tell you what is the maximum sign that you are able to put it without breaking the tension, making it safe. So that's really just substituting the maximum tension in this equation, and you can solve for what is the mass, the maximum amount of mass you can put on the beam. All right, so that's one example, very, very common classical example you will see in these type of questions. There is another static problem, is again very similar. I will simply go through it. We can go through it together, and I have everything written out already. Okay, so let's look at this. We have a sign again, but now like I move the sign not all the way to the end, but it is attached to 3/4 of the way out of the wall, okay? And the tension now is moved all the way to the end. Okay, and again, the entire length of the beam is L. The tension making the angle 60 degrees relative to the wall. And the mass of the rod is given as M and MR. So what is the tension in the wire and the force of the pivot? So this is the pivot. So you can see that it's slightly modified, but pretty much exactly the same as before, right? Okay, so we got a request to go back 2 slides real quick. I put it up here. Is this the correct slide? Okay, all right, can I move on to that next slide?
Can you go back a little bit further? Sorry.
Okay, here. This is just me writing out the process.
No, it was for the tension.
Oh, here?
One more.
Oh, here?
Yeah, thank you.
Okay. All right. Can I move on now?
Yeah, thank you.
Okay. All right, so let's go to take a look at this question. So you can see these two, I wouldn't consider these two are different questions, right? Very similar, simply the sign are moved at a different location and the angle is different. Okay, so let's go through that process, what we just did again, but now more accelerated. First of all, we want to draw an extended free body diagram, okay? To draw extended body diagram, we start out with the gravity, knowing that the gravity of the beam is right at the center, right? A gravity of the sign pointing down. Tension would be along the direction of the rope, right? Always along the direction of the rope. So right here, this is your tension. Again, the force from the pivot, we don't know exactly where it's pointing at. We can write down the X and Y component. Okay, call it X and Y force from the pivot. Right now here, we do know that the tension is at the angle, is not horizontal, right? Our tension before is purely horizontal. Now is at an angle. We know this angle is 60 degrees, so we can write down the X and Y component of the tension by breaking down that tension into 2 components. Because we know eventually we want to add up all the forces in the XY component and make them equal, right? So the X component is T cosine 30 and Y component is T sine 30 degrees, okay? Because this would be 30 degrees, okay? So here is our extended force diagram. And then we can try to put it into our force and torque equations. The force equations are straightforward to write down because all the forces in the X component are just the 2 One is the X component force from the hinge, one is from the rope, right? So they have to add up to be 0. And also vertically, you have 4 forces. The tension and the hinge both provide one vertical force, and then they have to balance out the gravity downward. All right. In the torque equation, again, we would like to pick the hinge as our rotation point. So there is no torque from the hinge that needs to be added. So the weight, the distance for my gravity of my beam, the rod is L/2, right? Okay, so you have force times L/2, it's negative. And again, here, the distance for my sine is 3/4 over L because the sine is put at 3/4 of the way out of the wall. So that's 3L, 3/4 times L times gravity. Again, that's negative. In terms of the torque from the hinge, you can see I need T sine theta and multiply by the entire length L, and that's positive. So you have the last term. And you can see that, well, this one will be able to give you tension right away. And these two will give you the hinge force in the X direction and the Y direction with respectively. So very similar to the previous problem we did, okay. All right, so that's all the force, the static equilibrium problems we're going to do. So remember, the actual problem may look different, right? Instead of maybe horizontal, maybe the whole thing could be vertical, something being balanced. Instead of mounting on the wall, they could be mounted on the ground. But you can see the process is the same. Draw your free body diagram and set up your torque and force equation. You want to choose a hinge point where you can be able to eliminate a force, make your calculation simpler, monitor the number of the unknowns with the number of equations so you know if you need one more equation to solve the problem. Like if I only ask you what is the force and the tension, you can just use the torque equation and you will be done, right? You don't need to set up the force equation. Lastly, I want to end this entire chapter by take a look at the Leaning Tower of Pisa. That is a famous place in Italy, right? And it's tilted. So how come the tower does not fall? Are we able to use static equilibrium to help us understand that? We know that that is a building structure, and we talked about all of these building structures has to be in static equilibrium. The forces has to be 0, the torques has to be 0, okay? So will we be able to use that to explain why it does not fall? Anybody have any thoughts that they would like to contribute?
I mean, I don't know if this is quite the answer you were maybe looking for, but it could be something as simple as the fact that the torques are balanced on everything, and like that its moment of inertia is so high that it's not currently like when we studied the bases, and it was like as long as the center of mass is somewhere along its bottom base, like over it, it won't fall. It could be that its center of mass, its moment of inertia is so high, and the center of mass happens to be over its base, so it'll just not fall.
That's very good. That's exactly the point. We wanted to demonstrate the torque is indeed balanced, right? So we want to think about, okay, the torque is coming from where? Coming from gravity of the tower itself and the normal force provided by the base Of course, it's not really just a tower set on the table. You still have all these concrete structures. So it's more than just a normal force, but we can use a normal force as sort of a simplification in our model to explain. And you had mentioned the rotational inertia. I think your point was that you wanted the center of mass to be low, right? Because we all know that when you have a lower center of the mass, you are more sturdy, you're more stable. Otherwise, if your center of mass is high, you're more likely to tip over. Why is that? It's exactly what Juan had just said. The tipping over point is when your gravity is shifted out of your base. So when gravity is still within the base, you will stand. But if your gravity shift over to out of the base, then you will definitely fall. So here I've shown you the different tilting points, or you can see that by moving your center of mass higher is also equivalent to tilting over more, that the gravity is out of the range of your base. So if you look at the sort of one of the standing situations, so you can see, okay, the force, it's easy to balance the forces. You have gravity, you have normal force, right? So that's easy to balance. We also need the torque to be balanced. So you can see that right now, if I'm thinking, okay, I have a normal force, I have gravity, the torque it generates, it is balanced. The torque from the normal force is sort of trying to make it tilt this way, and gravity is also trying to tilt this way. So if it's stable, because if it falls, it just falls back down, right? It falls back to the horizontal place, because both of these torque right now is trying to move this whole object back to its base, is in the counterclockwise direction. All right. However, if you can see your gravity, if it's shifted away from your base, normal force is on the left-hand side of your gravity. And you can see right now the gravity will tilt it over clockwise, and the object will not be able to return to its static equilibrium position. And if that's the case, you'll definitely simply fall down. Okay, so despite Leaning Tower Pisa looks so tilted in our eyes, its gravity from the center of the mass is still fall within the base. So it is stable, and it's unlikely to fall in the future. But the tilt does seem to increase over the years in history. It has increased the tilt a little bit, but it's still stable. All right. Okay, so that is this concludes our discussion for static equilibrium. Our next topic is universal gravity. Sorry, I have these two extra slides here. Is universal gravitation. People always begin the story by saying that it's Isaac Newton who inspired by the falling apples from the tree. That he was sitting down at the tree of the apple tree, and the apple fell onto his head. And from there, he got the inspiration. I don't really know if that story happened. It was an apple tree who was sitting there, but he certainly was the first one to relate two totally different phenomena together, right? We know that by doing physics, what we're trying to do is we're trying to seek principles and simple patterns in the chaotic phenomena around us. So for example, in the case where we are on Earth, we see objects fall all the time. Apples fall down the tree. If you jump down from somewhere, you always land on the ground. We all experience gravity, but it was first by Isaac Newton to realize that the force that is responsible for the falling apples is the same force that is responsible for keeping the planet in orbit. The moon is orbiting around the Earth, right? Because of the gravitational attraction between these two, and the planets, including the Earth, orbiting around the sun. That is universal gravitational attraction between these two, between the Earth and the Sun, or between the Mercury and the Sun, and so on. So he realized these two are actually the same type of force. The physics nature of that is exactly the same. Before him, many years before Isaac Newton, Kepler had made observations about the orbit of the planet, and he came up with Kepler's 3 different laws describing the motion of the planets. And now after Isaac Newton, we can explain all of these motions using the gravitational attraction. So some of the questions to start out with the discussion could be, if the planets are orbiting around the sun, what kind of force is keeping them in orbit, right? What kind of force is keeping the moon in its orbit? And could the force of gravity be universal? Some of these questions could be, might be where Newton started his thought process and came up with these conclusions. Now we know that you guys are able to answer these questions. For example, why would not the planet for moon fall into the earth, right? Why would not the earth fall into the sun? Because we have studied circular motion before, and we know that like the roller coaster, it's not gonna simply just fall down from the highest point because it has that velocity. So the force, instead of making something fall, the force simply serve to change the direction of the velocity, simply changing and keeping the object in the circular orbit. So that's why they don't fall, right? Because it follows a circular motion, a motion that you guys can all explain. So what does Newton's laws of universal gravitation tell us? It says any two objects attract each other with a gravitational force. So any objects with a mass. So there are forces between you and the earth. There are forces between you and your table, because any objects with masses. There are forces between you and another human being because you have masses. There are forces between your phone and your laptop because there are masses. There are attractions between any objects that has mass. And that force is proportional to the product of the masses. So if you're evaluating the force between the moon and Earth, this force is proportional to the mass of the moon times the mass of the Earth. If you're looking at the force between you and the Earth, and the force is proportional to the mass of you and the mass of the Earth. And that's inversely proportional to the square of the distance between them. A lot of times we describe such a law called the inverse square law because we see this here in gravity, and later on in E&M, we see that's also an inverse square law to describe the force between charged points, charged particles, point charges. So as distance increase, the force will reduce by 1 over r squared. So it falls down really quickly as the distance increases. This is a 1 over r squared dependence. And the directional force is simply in the direction of the line that connects the center of the mass between these two different objects, right? So we have a random object here and a random object there. This is the center of mass. This is center of mass. The force is simply along the line. Okay, so this is the universal gravitational force between these two objects. It's always an attraction, okay? So it's always an attraction. To represent this using mathematical formula, we will say the force between two objects, of course, they're equal, because if one attracts two, then two attracts one with the same amount of force, right? That's Newton's third law. So these two forces are equal, and that attraction is equal to the product of these two masses and is inversely proportional to the distance squared. And there's also a constant. This is just a constant. This is the gravitational constant, capital G. We have little g, right? We were saying the gravitational acceleration on Earth, that is little g, is measured to be 9.8 meters per second squared on Earth on average. And this is the universal G. And people also measured the universal G by doing a lot of experiments. We will be able to take a look at G later, and it's a very small number. Okay, so the only noticeable attraction that we can feel on Earth is our gravity exerted by the Earth, because the Earth has a very large mass, right? So when you multiply G by the very large mass, you have a force. That is your weight. But you can see that all the other objects, how come we don't notice anything else that's the attraction force around us? That's because the G is very small. And also all the other objects compared with mass of the Earth, all the other objects have very small mass. So the other attractions can be ignored. So we only consider our weight from the attraction of the Earth, but not from any other objects. Okay, so how do people in history measure this little g? We said the g is so tiny, right? And if you have just any random two objects, the attraction is so small. So here I want to briefly mention the Cavendish experiment because that kind of technique has been used in a lot of things in physics and other science experiment. Is he used something called a torsion balance to measure that little g. So basically we say that the attraction is so small. How do you detect it? The torsion balance allow us to magnify a very small effect into something much bigger that we can measure. So this is what the torsion balance do. You have two little objects mass here. So we know that if you have another force, another mass close by, it's going to create an attraction, right? So we put two other objects, a big M here and big M here. One is behind the M on the left-hand side of the balance, and one of the M is in front of the M of the balance, okay? So you can see the force on the left-hand side is trying to drag it sort of inward into the page. And the force on your right-hand side is attraction. So it's drawing the little m on the right-hand side outward, okay? So what does that create? One force pushing in, one force coming out. This creates a rotation. Give it a torque, right? Both of these torques is in the direction of making it rotate clockwise, right? So, and here you have this cable, whatever, very nicely accurate string, so that even though the attraction is so small, there's still a little twist to this cable, okay? And when you shoot up mounted a little mirror on this cable, when you shoot up a laser into the mirror, you can see just a tiny little bit rotation, a twist to the cable due to the gravitational pull is able to move the reflection of the laser beam by a significant amount that is allowing us to observe. So this is sort of a thought behind this, is something small, but we made it into something more noticeable using this torsion balance. Okay, so by doing such an experiment, we measured the Cavendish measured the gravitational constant in 1798. But of course, people had continued to repeat that experiment and improve upon the measurement of G. And the value of G, as we all agreed upon today, is 6.67 times 10 to the negative 11. And the units for G is simply whatever units to make this equation correct in terms of the dimensional analysis, right? This is newtons, and this is kilograms, and this is meters squared. So your G has this unit, okay? And you can see G is very small, okay? The gravitational force changes with distance and it drops as an inverse square law, right? It reduces as 1/r squared. So as your distance increase doubles, your force will become 1/4, right? Your force quadruples, your direction, your distance quadruples, your force will become 1/16 from what it had before. So it's, we call this a inverse square law. When you do 1520, you will talk about Coulomb's law, that is the force between charged particles. That is also an inverse square law, 1/r squared, and as you will see later. Okay, and we said G is so small, which makes the gravitational attraction are very, very tiny on an everyday object, so that we don't have to worry about all these gravity we are feeling from the other objects. For example, if you try to plug in the G and using two masses, for example, the person, you can use the mass of the person and a mass of an everyday object. Let's say your backpack. Assume a mass, and this is actually a pretty big mass for a backpack. And you can see you get a very, very tiny gravitational force from your backpack. It's so tiny that is negligible and you don't have to worry about it. Okay.
Can you go back to the previous slide, please?
Here?
No, the one before that one.
This one?
Yeah, that one. Thank you.
All right.
I got it.
Okay, all right. However, this force cannot be ignored if you're looking at astronomical objects. So our Earth is such an astronomical object. It has a very big mass. So that make our forces, our weight to be not negligible. All of us have a gravitational force acting on us, and all the other objects has a weight, right? They all have weight. Why is that? Because the Earth is giving us a very much bigger mass. So for example, if you do that to do an estimate of, okay, how much force I will experience on Earth, you would get 700 newtons for a 70 kilograms person on Earth. Okay, so that is not negligible apparently. We will do a little more practice to compare this number to what you would have got with m times little g. You know that on Earth, our weight is simply m times little g. The mass of the person times 9.8 meters per second. So you can see that's very close, right? Because our mass is 70 and g is almost 10, right? So when you multiply them together, you get 700. All right. So let's take a look at this question you have already done. We have 3 different diagrams representing the gravitational attraction between the sun and the Earth. These little blue dots represent our Earth, and the giant yellow dot represent our sun. Okay, so which one of these diagrams is correct?
I think B is, because the force arrows, vector arrows, are the exact same for both of them.
Yes, very good. What is different from this diagram with the rest of the diagram is this attraction is neutral between the sun and the Earth, and they have to be the same magnitude. Right? This is way small and this is way small, and that's wrong. Because we know this is correct because of Newton's third law. Right, object force from object A to B is equal and opposite direction force B on A. And in this case, the attraction is neutral, and that attraction is proportional to both of the mass combined and the distance squared, right? So you can see that the mass of the Earth and the mass of the Sun both enter into the picture divided by the distance squared. So it is the same formula describing these two forces, and they have to be the same magnitude. But if we were to compare the acceleration, and we have done similar questions in Newton's third law chapter, right? We know that, well, obviously, the mass of the Sun is much, much more than the mass of the Earth. So such an attraction on Earth will create a much bigger acceleration of the Earth. That is responsible for keeping the Earth in the orbit, but the gravitational force from the Earth to the Sun barely did anything to the Sun because the mass of the Sun is very large. So the acceleration of the Sun is so much smaller than the acceleration of the Earth. So because we used Newton's second law, right? All right, so that's all we're gonna have time to do today. Wednesday, we will continue to talk about universal gravitation. All right, I will see you guys on Wednesday. Have a good rest of your week.
I'm sorry, I have a question.
Yeah.
So I was looking at my homework, I guess, and I didn't see any pre-labs or bridge questions for this week. Is that
is it not in there? Let me check. Okay, let me see.
Yeah, there were none due on Achieve for today.
Okay.
Yeah, I thought it was because our homework 13, I think it's from, I don't know, it's angular momentum. So I thought it was with the pre-labs that we've already done. Like just because using some of the old ones, because I don't think our homework has dealt with all the new ones yet.
Okay. Yeah, I don't see any. Let me double check, because we had sort of a system. We had actually moved to Achieve from a different system before. The content was the same, but now it's presented in a different format platform. That's the Achieve. So it is possible some of the stuff did not get moved over. Let me see if I could add it back for Wednesday, but if not, don't worry, I will just present those bridge questions. We will treat them like new questions, so we will have some time to do them in class then. Thank you for letting me know. I had thought that they were all there.
I have a quick question as well.
Yeah.
So for the homework yesterday, I completed all of it, but like on Canvas, it like graded it and it said I got 6 out of 10. Will it just like automatically update later during the day?
Yeah, it uploads automatically. I've noticed the same thing. So
Okay.
if you stop doing the homework for any like brief period of time, it'll eventually like it'll go to that score, but then once you keep doing it, eventually it'll just fix itself automatically.
Okay. All right, thanks.
Yeah.
Okay, thank you for letting us know. I have noticed that because sometimes people ask me that their homework seems to be a lower score than they think they should be, and I check it on my end. I check my grade book. It shows to be 100%. So if you still worry on your end, you can always ask me and I can look it up on my grade book for you to see if it's correct. All right, any other questions?
Professor, can you go back? I believe it was 2 slides.
Okay, here.
Sorry, one more.
Here?
Yeah.
Okay.
Okay, thank you, I got it.
All right, I'll see you on Wednesday, everyone. Bye-bye.
Bye, Professor. Thanks. See you later.
Bye.
Thank you, Professor. Have a good day.
Thank you. You too. Have a good day yourself.